from where we left. And a lot of things have been changed. We used to have one day of the week in person and another day of the week virtual, so as to balance things up. And we agreed by a majority decision that our Mondays are going to be the virtual classes and Fridays are going to be in-person classes. And as and when anything changes along the line, you'll be duly communicated so that at least you can make the necessary adjustments. But whatever being the case, we are going to follow this schedule. And I mean, it's been a while. Probably some of us have become a little bit rusty with some of the things that we started with. So today I'll take it very easy and make sure that we are at the same pace when it comes to the things that we need to know. So quickly, I'm going to share my screen with you and we are going to start right away. So what I'm going to do first is I'm going to share a GitHub repository with you like we always do so that you can also have access to the materials that we will be working with. So that's in the chat. You can have access to it. And let me quickly do this. So in our schedule, this is what you have been working with. The last time I could recall, we dealt with the Python programming. We looked at the data preparation for ML models. We also looked at how we explore data, do some basic analysis on data. And we also saw how we could generate data for ML models. Then we did some preparation, finding class imbalance. These are things that we need to cover a few things before these ones become necessary or relevant. So we are going to come back to this. But then we've also seen a little bit of data visualization. We have also seen, please, the noise, I'm getting feedback. All right. So we're also going to see the feature importance and relevance plots and data encoding. At least we saw a little bit of data encoding where we're changing some textual values or data into some numerical values in order for us to work. Now, we were able to at least build some model, do some training, do some performance analysis, at least a little bit of it, and also do some model testing and evaluation. We are going to go in depth based on the things we'll be doing along the way. Now, we didn't touch on, we didn't touch on the Google Colab and TensorFlow. I'll quickly do that today and we'll move on to some of the things that we need to do. So based on our schedule and everything we've done so far, we've been working on our local computer. And for some reason, there is a service that we can use called Google Colab, okay? So I'll just do a Google search on this, Google Colab. When I press enter, it takes me to this website. Of course, you need internet for this to work. So you have Google Colab over here. When you click on this link, I mean the very first one, and I believe the link is colab.google. It takes you to an environment where you can start writing your code. Over here, it gives you an environment where Python is already installed. Most of the libraries you will need are installed. So you don't have to do the pip install, scikit-learn, Keras, and all those things that some of you had issues with. So if you have very good internet, you can straightly go onto Google Colab and work. But then if you don't have internet, then you'd have to do the installations you've done on your computer now, and whether you have internet or not, you can work. So over here, it says I should open Colab or new notebook. And I also need to sign up. So let me try signing up over here so that I can quickly go through the process. All right, so I think we have, I don't need any of these. These ones are too expensive. There's a free version actually, and I don't know why. No, let me just close this one and just open a new notebook. This should open very soon. I don't know why it is taking forever. All right, so here we are, and clearly you could see that we have that, interface that we can work with. Okay, over here too, you could see that it has some AI that's been embedded quite recently. So a lot of the code that you probably would be writing, you get some help here one way or the other. So this is the interface that we get. Let me just collapse this. And there's nothing different from what we were doing previously. So let me just open up this and CMD, open up in Jupyter Notebook so that at least we see the comparison. So this on my local server, which we have seen over and over again. I have most of the libraries I use installed on my local computer, and I don't need internet for this one to work. But then with Google Colab, I need internet connectivity. So yes. So what I'm going to do, I'm just going to create a new notebook. And I think I'll select a kernel. So this environment we are quite used to. We have been writing code in here over and over again. Now, Google Colab is giving us the online version, so to speak. So almost everything we can write over here, that will work. When I do it over here on my local system, it's also going to work. But the interesting thing is over here, I don't need to install any library. So right away, if I'm to do pip list and do a shift enter, like we used to do, this one has libraries pre-installed. So I don't need to bother myself so much with the installation that I did previously. So it is going to list quite a number, okay, of, and these are, I believe, the most popular machine learning libraries that people use. So almost everything that you probably need is here. However, if you need an extra library that is not listed here, you can still do a pip install and then it will be added onto the list. But I think it is not going to stay on forever. I think once you log out, it is taken out of the cache or something like that. Right. But at the very least, most of the things you need is pre-configured for you. Now, one interesting thing that you can also have is, I think this, yes, no. When you click on these files, you see that we have sample data over here. So you can have, all right, so you can have some sample data you can work with, and we are going to later on work with this particular one, which is the MNIST data set, okay? And there's a California housing data sets. So you can simply do some data manipulation and a few things over here. So if you want to import this, remember this is a CSV file, and it is located in the sample underscore data. So over here, I can simply do something like import pandas as PD. I'll run this, and pandas is pre-installed for me. So I can say, okay, my data is going to be equal to pd.read underscore CSV. And the data that I want, you see that over here is kind of giving you some help one way or the other. But then what you need is inside of this folder called sample data. So inside of this, you have sample underscore data slash, then probably you see that over here gives you that autocomplete thing over here. So if you want the California housing underscore train as it has been auto-completed for you, you can just, I think, press on the tab key and it will just pick it up. So when I do shift and then enter, this is loaded over here. I can now do a preview of this, get to see the data set, and everything that you probably were doing on your local machine, you can do it over here. So this is more or less like some kind of a fast food kind of a thing for you. Okay. All right. So this is it. Now, the few things that we need to know is, okay, so with Google Colab, TensorFlow is already installed. Okay. And the whole concept of Tensor is where we are actually getting Keras to also build these deep learning and machine learning artificial neural network models that we are building. Now, when we say tensor, tensor is an interesting word. Okay, so let's look at the, not TensorFlow, just tensor. Tensor in itself is a multi-dimensional array of numerical values. So normally when you have data, like we have the vector quantities and the scalar quantities, we know that the scalar quantities are just quantities that has no direction. But then a vector quantity will have magnitude and then direction. Now, that's almost as if you are going a layer above, or you are going a degree above in terms of the quantity and the direction. Now, what happens with tensor is when you have an array and you go a layer above, or you increase the dimensionality, you get what we call a matrix. Because, and the array I'm talking about is like a row array or a column array. Okay, when we go a layer above, then we are getting multiple rows and multiple columns, so we have a matrix. Now, when we go a layer above a matrix, then we are going into the realms of tensor. So tensor is a multi-dimensional matrix, so to speak. And the reason why we need tensors is because of how complex some data can be. Okay, later on we are going to see how images are formed and how tensors are even more relevant. So Google built this library called TensorFlow, where we have all the, I mean, most of the deep learning and machine learning libraries that we have been using. Okay, now with that out of the way, at least we've seen a little bit of TensorFlow. We are going to use it even today. And the setup and the configuration, we've done the installation some time ago. So at least that is already set. And then we have the model creation, initialization, training a model, saving a model and reusing it, and then the model deployment. So these are things at least we've touched on in bits and pieces. Okay. Now, what we have over here in the subsequent chapter, which is the introduction to neural networks, we've also touched on a little bit of this. So we've seen the perceptron and the shallow neural network design. Then we looked at the network training process, the classification task. Later on, we are going to see the regression task. Remember, before we ended or we took our break, we dealt with a little bit of trying to build a network model to classify the appropriate class, whether it is Iris Setosa or some things like that. All right. So today, what I'm going to do is we are going to touch on these ones over here and at least fill the gaps. Okay, since it's been a while since we last met. So what I'm going to do is, first of all, let's just a minute. Okay, I'm back. So today we are going to fill in the gaps and see where it all fits together. But before we can do that, let's look at the perceptron. The perceptron is an interesting concept, and we've already come to appreciate what this neural network is all about, taking inspiration from the biological human brain, blah, blah, blah. Now, what I have over here, and with the link I've shared with you, when you download it and decompose everything, you are going to have this notebook file that is inside of the perceptron repository. So over here, we have an idea based on the things we already know that, okay, the neural networks that we build, or the artificial neural networks that we build, the whole concept is we are inspired by the biological human brain. So the biological human brain has these building blocks called the neurons, okay? And a typical neuron will look like what we have over here, where we have the nucleus. It has dendrites. These are basically sensors that takes inputs or some signals, okay, to be more technical. And it has some axon that's also connected to other neurons and stuff like that. So this is what's probably under a microscope. You take a piece of the brain, this is what we are going to see. But then mathematically, or using some engineering principles, we get to have this. So now let's go back to what we have over here. This is a very short note. We are saying that the engineering model of a neuron refers to a simplified practical abstraction of how the biological neuron functions. So it is just an abstraction. It is not really dito what it does. Okay, we've simplified it and we've abstracted a lot of things in there. Now, the engineering model is developed for use in the artificial neural networks. Now, this involves breaking down the behavior of the neuron into computational components that can be easily implemented in machine learning models. So now you see that the image shows the biological neuron and its equivalent engineering model. This we've seen over and over again. Now, we've also come to appreciate that within a single neuron, you have inputs coming in. Over here, we are representing this with X1, X2, up to maybe Xn, depending on the number of data we are accepting. And we may also have some biases along the line. Now, there's going to be a linear function, which is a summation operation, and after which it is going to be passed through an activation function for us to get our inputs. So the objectives of what we have over here in relation to we trying to understand the perceptron, okay, and also the shallow neural network, and also it shall be well, bro. Please, I'm getting feedback over here. Cyril, and I'm trying to mute you, but it's not even working. So please, kindly do us the honors, mute yourself, and let's maintain decorum here. All right. So we are going to look at that perceptron, okay, how we can critically look at it and perhaps maybe write our own code to do some computation, not just taking something from Keras or any other place. So today we are going to go a little bit back, understand the basic concept, and now move forward as we intend to do. So we are going to learn how the parameters, because we know that within this we have the weights, we have the biases, and we have the activation function, enable neurons to process inputs and generate outputs. So we are going to learn how these parameters work hand in hand. And we are going to explore how adjusting the parameters can also shape the decision boundaries of what the neuron will give us. And we are going to use the neuron model to design and simulate logical operations. So we are going to have the simple OR gates, the AND gates, and instead of we knowing that, okay, if typically I have an OR gate, I have one input as off and another input as off. If there's an OR gate, then the resulting output is going to be off. We want to train a perceptron, okay, that single layer neuron to do that computation for us, to make that prediction. And we are going to see how we go about that. Now, at the heart of everything we are going to do, yes, there's going to be this mathematical foundation. And the first formula we need to worry ourselves about, which is not so much of any big formula, is this linear function we see over here. So we are going to have a function, and that function is going to be what we have over here. Basically, the activation function, everything is going to pass through, okay? But then we are going to have the weights and the biases coming in, and we are going to have the weight transpose. Later on, we are going to see why there's going to be a transpose, because if you have matrices multiplying things, you need to be minded about how things are, okay? So you're going to have the weight multiplied by the inputs. Normally, our input is going to be, in this particular instance, is going to be the inputs from the X. Okay, so on, then we expect an on if it is an AND gate, basically that. Then we're also going to have some bias, and the weights are going to be randomly generated values that we have been seeing. Now, the activation function is very important, especially for this particular exercise that we want to do for the logic gates, because with the logic gate, our expected outputs, let's look at this, our expected output is either going to be a 0 or a 1. So a lot of the time, we've learned about different activation functions, and indeed, we are even going to learn more. But then the point is, it is not just going to be guesswork. Okay, we are engineers, so every decision we take should be informed by some fundamental mathematical logical principle. And the logical principle we are using over here is our output is either going to be a 0 or a 1 for logic gates. Therefore, the activation function, which is going to be at the very last end of whatever thing we want over here, should reflect that kind of output that we need. So in this particular instance, we are saying, okay, over here, we are going to use the unit step function, because the calculation that will result out of this can be any number. It can be 1, it can be -2, it can be 3. But at the end of the day, we want our output to be that 0 or 1. So with this unit step function, we are saying that, okay, if the output from the calculation we have over here, if it is greater or equal to 0, then we set it to 1. But then if it is less than that, then it should be 0. So over here, we see that it is going to be 0 if the output from that target is less than 0. So maybe a negative, after this calculation, if we get a negative 3.5, it is less than 0. So we are saying that just make it an output of 0. If it is t is greater than or equal to 0, if it is a positive 560, we are not interested in 560. We are saying that if it is any positive number, then put a cap on it and present 1 for me, because we are using a logic gate. Logic gates will only have 0 and 1. They are just binary inputs and output that we expect. So at the end of the day, we are saying that within the context of logic gates, the output of an operation is either a 0 or a 1. All right. Now, the process of whatever thing we see over here, it isn't just not going to be one time operation, okay? Probably there are going to be a number of iterations that the system needs to get through, because if it is just once, we may end up not getting good enough results, because we want to be propagating back the error to be doing the updates of the weights. So in updating our weights, we have this simple formula over here, and it's saying that the new weight, okay, or the new weight is going to be that weight plus the updated weight. So the new weight is going to be that weight plus the updated weight, where the change in weight is going to be equal to our target minus our output multiplied by the input itself, and then we have our learning rate showing up over here. And I believe the one of the last things we did before we took our break was to see how relevant some of these things turn out. Excuse me, just a minute. Okay, thank you. So what we are going to do is, the activities are listed out over here, very simple. We are going to write the code to implement the logic gates, so that we are not hard coding. We just want to give our system or our computer or whatever thing that we write the data, and it will learn and make predictions for us. All right. So we shall use NumPy. So NumPy is only is going to be the only library that we are going to use. So everything else is going to be something we are going to write ourselves. And let me just say that this is just going to be a perceptron, just one neuron architecture that we are going to build over here, okay? It becomes a little bit complex if we decide to add more neurons to one layer, then the mathematics becomes a little bit complex. So we are going to limit ourselves to just the perceptron. So what I'm going to do is I'm going to write the code over here. So kindly bear with me, and I'm going to explain at every step of the way. So we are going to write, we are going to use the object-oriented programming approach. So we are going to write a class, okay? And let me just start over here. So I'm going to say class, and I'll say perceptron, and then I'll press enter. So there will be an indentation over here, obviously. And then we have to give it the init method. And inside of this, we pass in self, because self is pretty much a constant we need to pass for every method we write under a class. And then we also need to have the learning rates. The reason why we would need to have the learning rates is because of the updates that will be done along the way. So our learning rate, and let's set this to an initial value of, let's say, a 0.01. Remember, if the learning rate is too small, then the convergence of it is going to take a while, okay? It's going to be computationally expensive. If it is too big, then we can miss the optimal point based on that illustrations that we know. Then what we also need is going to be the epoch. So the epoch is going to be the number of iterations. So over here, let me set out an initial epoch of 100. So these are going to be parameters that we can change, okay? But then we are setting out initial values over here. And now let me complete the rest of the init method. So over here, I'm going to say solve dot, we know our learning rates is going to be equal to our learning rates. Then solve dot our epoch. Sorry. Control C is going to be equal to our epoch over here. Then we would also need to write something about the activation function, okay? Because at the end of the day, whichever calculation that is done passes through an activation function. So what I'm going to do over here is I'm going to say solve dot activation. Okay, so solve dot activation function should be equal to the activation function that we are going to define, okay? But that one is going to be a function of itself. So I'm going to say solve dot activation function over, and this is what I mean. So that's going to be a method under this. So I'm going to call this def an activation function. And this activation function, because it's a method under this perceptron class, is going to take in solve. And now look at this. It's going to take in a parameter, and the parameter it takes is going to be something from, the computations we do over here, okay? Something from the computation. So it's going to take some X value. So let's just put X over here. And then I'm going to say pass. We are going to come back to this, but let's complete what we have over here. So we are saying that that activation function method is going to be activated over here for the computations to be done. Excuse me. Okay, so this activation function will be called in order to perform this computation that we see over here. All right. Now, there are some few things that we also need to take care of, because we also have to get our weight. So I'm going to say self.weight is going to be, now I'm saying none. And the reason why I'm saying none is because of the fact that the weights can change depending on the data that we present. So if we present a logic gate of 3 inputs, then the weight that needs to be generated, the dimensionality is going to be different from if it is a logic gate of 4 inputs. So that's the thinking I want us to have over here. And now you also want to have the bias. So I'm going to say solve.bias is going to be also none as well. So at least we have this going and everything looks good over here as far as I'm concerned. Now let's concentrate on this activation function. This activation function is going to be such that, okay, if whatever input we get out of the activation function is less than 0, it should return a 0, else it should give us a 1 based on what we see over here. Now, in order to get this working properly, let me just, let me work this out over here. So we have the activation function that we are trying to write over here. Now over here, I'm not going to put self over here because it's just a standalone function, okay? So it is going to take some inputs. And just as we used to do when we're doing the if-else statement. So I can say that if the x is less than 0, then, for instance, maybe I would want to print the output is equal to 1. So, sorry, 0. So I'll say 0, okay? And then I'm going to say if x is greater than or equal to 0, then I would want to print 1 over here. So this is a logic that we want to implement for our activation function, especially for the unit step function. And the reason why we are selecting this is because at the end of the day, the output for our logic gate is either going to be a 0 or a 1, no matter how we look at it. We are never going to get a negative 3.5 or a positive 160. If it is 160, we want to cap it to 1. If it is a negative 3.5, we also want to cap it to 0. So that's what this logic is working out for us. So now let me just run this. Now, if I'm to call this function, Control C, and for instance, pass in 100. Now 100 is greater than or equal, so this logic will kick in. So at the end of the day, I'm expecting to see a 1 over here. So I get a 1. Okay, let me call this function again. If the input I give it is negative 0.664, this is going to activate this block of the code in terms of the logic, because what I have over here for x is less than 0, so it is going to print out 0 for me. So now when I run this, I get 0. This is what we want for the output end of our logic gates. But then if you write it this way, we are going to have a little bit of some small issue, okay? And that's simply because, or that's why we need NumPy to make things work, because NumPy, anything that deals with numbers, we can follow NumPy. So let me just show you what I'm going to say. So I'm going to say import NumPy as NP. And from these imports, let me rewrite the function again. So I'll do a Control C over here. And now what I want is, okay, I don't want to have just printing 1 and 0. But then let's say, what if I say, okay, so return, let's say np dot array, and the value I want over here is 1, okay? And else, let me say return np dot array, and the value I want over here is, no, this should be 1 and this should be 0. Okay, so let me run this, and now let me call this function again. Now, when I pass in 100, I'm not just getting a 1, but then I'm getting an array, because we'll be doing computations one way or the other with this. And if it is an array, NumPy definitely will know how to work with it. All right, let me run this again and give it an instance where we have a negative 19, and this is now giving me a 0. So basically, it is the same thing, but just that this time around, I'm using NumPy array. Now let's even make this better in terms of what we want to do. And I'm building this app because I don't want anybody to get lost along the way. So I can actually shorten whatever thing I have over here in terms of this, okay? So what I'm going to say is, okay, so instead of the logic we see over here, I'm going to simply say return np, which is our NumPy dot, and I'm going to use how do you call it? A method in there, which is also going to almost work like list comprehension. Okay. Later on, we are going to see list comprehension over here, but then all that I'm saying is, okay, now return np dot where, and I'm going to say if x is greater than or equal to 0, what I'm saying is return 1, else 0. So the long thing I did over here, I've just put it in one line. And like I said, this is almost like list comprehension. Okay, so now when I have it this way and run it, we still don't have any problem, because if I come back here and come and do passing 100 over here, when I run this, I'm getting 1, an array of 1. And that's simply because if the x input I have over here is greater than 0, and indeed this is greater than 0, it is giving me a 1, else give me 0. It is either going to be one of them. So let's try this for the last time, and let's pass in a negative 0.99. This is less than 0, so when I run this, I'm getting a 0 over here. So that's the function, or the unit step activation function that we want over here. So let's come back here and come and complete that. So over here, I'm just going to say return np.where, and over here, I'm going to say that if x, like this is how you almost read it, if x is greater than or equal to 0, return else 0. It's very simple. It makes your code look very clean, and you don't have those indentation issues and stuff like that. So this activation function is definitely going to serve this purpose as we have over here. And the reason why we are selecting this is because of the fact that for a logic gate, we expect either a 0 or a 1 for the output, because right after going through this activation function, we are getting our output, and we don't want our output of 0.3. What is 0.3 to logic gates? It really does not make sense. Okay, so now that we have our activation function sorted out, now there are two main functions that we need to think about. Now remember, when we're building our models and we're using what NumPy, sorry, what Keras and TensorFlow had given us, it was almost like autopilot. So we were just calling the functions and working with them. Now we are going to write our own functions to mimic or implement that same logic. And we need two functions over here. So the first one that we are going to do is to write a function for fitting the model. Remember, we used to do model.fit. So when we call that fit method, we pass in our x and our y, and it does the magic for us. So that's what we are going to do over here. So model.fit is going to come in here. And for starters, let me just put self over here. And then let me just bring in pass. So at the end of the day, we are going to write this. And now we also need another one to do the prediction. So I'm going to say, we are going to call this predict. And this one is also going to take in self. And for starters, let me just say pass. But at least up until now, there shouldn't be any problem, okay? Because you are going to fit. So this is where the training is going to be done. And this is where, after the training is done, we'll call this method to be predicting new values that perhaps maybe wasn't used as part of the training, which we are going to see for ourselves. So now the prediction is pretty much simple over here, because at the end of the day, the prediction is actually going to be from this function, okay? So yes, the linear function will set in, where we are going to accept the, how do you call it? The input and the weight, do the dot operation, and then add the bias to it. So having said that, we can come in here and I can say the linear output is going to be equal to, please, just a minute. I'm getting some people are here with me making noise, so let me just. Okay, so we are going to write this linear, this linear function over here, where our W transpose multiplying our X plus our biases. So what we need over here is, okay, we need NP dots. Okay, I think this one, there was one that I showed when we're dealing with it's in one of the videos, okay? So we use the dot operator over here whenever we're working with things like this. And what we need is eventually we are going to, you see, when we are predicting, we'll be passing some X value. So that X value will come in here. We'll be passing that X value over here. And that X value is what we'll need to predict that kind of a Y for us. So we are going to do NP dots, and over here, I'm going to say self dot weight. Now, what am I saying self dot weight? Because weight is originally going to be here. Okay, weight is also going to come up here whenever we are fitting or training the model. But then we need a weight, and then we also need our X over here. So self dot weight and X is going to work this out for us. And then we'll do a plus self dot bias. So this is basically this linear output, how do you call it? Equation is simply what we have over here. Okay, the weight multiplying the X plus the bias. The weight multiplying the X, but because we are doing NP dots, this is how we go about it. And then we add the bias over here. Now, once this is done, we are going to get something like this, some Y predicted value. And that Y predicted value, we are going to say self dot. Look, whenever we do this computation, we need to pass it through the activation function. And the only way we get through the activation function is now we calling that activation function itself. So I'm going to say self dot activation function. And then what do we pass through? We pass this linear output through the activation function, because that's exactly what we want to do. Because at the end of the day, whatever calculation that's done over here, maybe it was 100. We don't want to see 100. So that value, when we pass it through the activation function, will now give us that logic. If it is greater than 0, return 1, else 0. So that's why we have this over here. And finally, at the end of the day, we'd want to return this predicted Y that we have over here. So this is a very simple one, and I believe this shouldn't be confusing. I think it's only the fit that has some iterations that may look a little bit funny, but then I think this one should be okay, because here we have the linear output, which is just doing a dot operation over here plus the bias based on the formula that we know. And now the Y predicted is now going to, whatever data we have over here, we are going to pass it through the activation function. Sharif, I can see your hand up.
Yes, please. Can you kindly explain the dot function once again?
Oh, the dot function. Okay. So, surprisingly, and I remember very well that on the day of, so let's come back here because this is where we are going to do the rough work. Okay. So I think let's say we have two arrays. Okay. So we have X is equal to NP dot array, and let's say we have this let's say a 2 by 2 array. So let's say we have 1 3 comma 4 9. Okay. Okay. The spelling of array. So this is my X array. Okay. And then I have my Y, which is also going to be NP dot array. And let me also have a 2 by 2. So let's say 5 4 5, and then 9 2. So this is my Y over here. Now, if I do NP, which is an NumPy, which we already have imported, dot, we are using the dot operator over here, or the dot summation. Sorry, the dot product, basically. So if I pass in X comma Y and run this, it is, I wish we had a marker over here, but the dot, the dot product for these two arrays, okay, I think it's going to be 3 times 4 plus, sorry, 1 times 4 plus 1 times something, then you get this 31. Okay. Now, the reason why we are not doing X multiplying y is that when we do x multiplying y this way, this is more or less like a broadcast. So it is only going to multiply 1 times 4. And that's why we are getting that 4 over here. And it's going to do 3 times 5. And we are getting a 15 over here. And it's going to do this 4 times 9. We are getting a 36. That's not what we want. So this is almost like a pairwise broadcast of the elements. Now, the problem arises, and what we actually need is a dot product. Now, the problem arises when, let's say, we have let's say a scalar quantity and a vector quantity, or maybe the dimensionality is a little bit different, okay? And the reason why I'm saying this is when I was speaking about that earlier on, you are the one who were like, oh, you remember that thing. So yes. So what I'm trying to say is, let's say we have another array Z, and Z is, let's say, np dot array. And this one, let's make this one is a 2 by 2. So let's make this a 2 by 3. Okay. So 2 by 3. So let's say we have 1, 2, and then we have 4, 7, and then we have 9, 6. All right. So now we have we have 3 rows, 2 columns. Okay. So let me see. So for X, it is a 2 by 2. And for Z, it is, the number of rows we have over here is 3, and the number of columns we have over here is 2. Okay. So let me rearrange this. Let me just get rid of this. Okay, so I want a 2 by 3. So this is what I want. I want a 2 by 3. Now, if we try to multiply this and just use, let's say, x multiplying z, we are going to have dimensionality issues because, yes, the x, let me just do it right away so that you see exactly what I'm talking about. This is our x, okay, and this is our z. Now, x multiplying z, we are going to have problems because it was trying to multiply this by its corresponding, it got 1 over here. It tried multiplying this with its corresponding, it got, but then when it got to the last one, it didn't find 1 over here. But then mathematically, trying to multiply this is possible, and it is only possible because you see the dimensionality of the column of the first matrix is equal to the dimensionality of the row of the second matrix, so it makes it compatible. And at the end of the day, we are going to get a 2 by 3 resultant matrix. So since this is not going to be possible because this is only a broadcast, we now have to do np dot and pass in x and z. So now when we do this, now we are getting that thing. Please, I hope this clears everything.
Yes, please.
All
Thank
right.
you very much.
All right, you're welcome. So that's exactly why we are doing the dots over here, because when we do the multiplication, it's just a broadcast and it's not really what we want. Okay, so now let's just make progress from here. So we do that dot and we are passing in the weights and also the x data, and then we add the bias over here, and then whatever output that we get, we pass it through the linear, the stepwise activation function that we've written ourselves and we've tested, and we've seen that it is actually going to give us some good results. So now let's go to the other half of it, which is going to be the training part. This is going to be where we are going to train our data. So with this particular one, it's very interesting. Now, let me also say that, let's say I have this data set, okay? And I'm doing this, okay, so let me just do from, okay, from sklearn imports, no, from sklearn.datasets, okay, datasets import import load underscore iris. Okay. So we know the iris data set very well. That's why I'm using this to help us appreciate whatever thing we are doing. So if I'm to do a preview of this, we get this. Okay, there's a data. Now you see that this also, at least with what we have now, this has been put in a structure of an array. Okay, now we know the iris data set. The iris data set very well. That's why I'm using this. Now we all know that, okay, this one is representing like something like sepal length, sepal width, and then petal length and petal width. Okay, now that's going to be the column names. So the column names are going to be the features, and the rows are going to be the number of instances that we have. I'm making a point over here. The columns are going to represent the features, and the rows are going to represent the number of instances. So over here, if I'm to do data.data, remember there's a dictionary, so I can just grab data, okay, and it's going to give me that entire stretch of data I have over here. And now, because of this, if I'm to do a dot shape over here, I get to see that, okay, I'm getting 150. This 150 is going to be the number of rows I have. And then the 4 we see over here, which is the column, is going to be the number of features. So that's what I want to put out over here. So now look at what I'm doing. I'm doing a dot shape over here to get the number of, how do you call it? The inputs and whatever. So over here, I can be smart about this and say, okay, I can say n samples, which is the number of samples, comma, n features, which is the number of features, is going to be equal to this. I know that this is going to be a tuple. I've decomposed this into these two variables I have over here. So now if I run this and do the number of samples, I'm getting 150 over here. And if I do the number of features over here, I'm getting 4 over here. We want to be smart about this, and we want to implement that same logic in here, because the reason why we want to do this is we want to have a situation where our system is a little bit dynamic, because we want to have an instance where we train our model or our network to have, let's say, input features of about 3. Remember, if the input features is 3 for a logic gate, the number of instances is going to be different from if the input is 10. I don't know if you understand the illustrations I'm making. Okay, what I'm trying to say is, if let's say you have a logic gate, and let me just use this. If you have x1, okay, as inputs, we have x2, and we have y. So this is just 2 inputs, 1 output. All right. Let me just copy this and let me just show you. If, for instance, this is an OR gate, okay, we can only have, let's say, 0, 0, 1, 1, and then we have 0, 1. I think digital circuits and all those courses, good. This is the number of, the largest number of inputs that we can have. We cannot go beyond this. But then if it is 3 inputs, then we are going to get 8 features, because the combinations are going to be different. If it is 4, we are going to get, I believe, how many? Is it 16 or 32? So you can imagine. So the point you are trying to make is, okay, we want to make our system a little bit dynamic in such a way that it is going to figure out the number of samples it is going to get. And what we have over here is, now when we are fitting our model, we pass in our X, which is the training data, and its corresponding Y. Of course, this is supervised learning, okay? And what we want over here is, okay, we want to dynamically figure out the number of inputs and the number of features that we have. And we are going to get that from the X. So look at what we have over here. This entire thing is going to constitute our X, okay? So now, based on what I have over here, when I do x.shape, it is going to say that, oh, okay, I have 2 features and I have 4 instances. So it's going to be 4,2, just as we saw with this particular example. So back to this, if I'm to do x.shape over here, if it is a logic gate of 2 inputs, I'm going to get 4,2. So what I need with this is I need the number of samples, and the number of features based on whatever thing or lessons we've learned from this particular one. So I believe this one makes sense. Okay, so now let's move on. So now that we have the number of samples and the number of features from X, what we can then do is, okay, then I can say self dot, for instance, weight is now going to be, I'm just now going to initialize. So I'm going to say np dot zeros. We are starting with 0 so that through the updating of the weights, the numbers will keep changing. All right. Now, how then do I even figure out the shape of that matrix?
That's the dimension,
yes,
of the matrix.
Very good. Now, the dimension of the matrix is going to be from the number of features that I have. So let me just illustrate over here. Now, at least with this one is very clear. We can see that we have 2 inputs. Okay. And we are saying that the dimension of the weights that we will probably want is, because at the end of the day, this is what is going to happen. It's going to take the first input, which is 0, and multiply it by some random weight, okay? Some weight plus the second input, which is 0, and then multiply it by some random weights. And what I want over here is, okay, I want the situation if the inputs are 3, that means I have 3 inputs coming in. So the number of features is very paramount to me knowing the number of weights or the dimensionality of weights that I need for my network. And that is why we are saying that, okay, for the initial weights, we are saying that, okay, we just want to initialize everything to 0. We are starting from the very basic 0, and then give me a number of weights based on the number of features that I have, because it's going to be multiplied by everything. And that's exactly what we see over here, especially with this diagram, because this is our input, this is our input, this is our input, and it is going to be connected with one single weight to the neuron. So if I have 3 inputs, I mean I want 3 weights. If I have 4 inputs, I want 4 weights. And it's only going to be determined by the number of features that I have over here. So this one should be also very simple for us to understand. Now, I have the bias over here, which I'm going to set to 0 because the weight is 0. The bias is also starting from 0. Now we are going to do the updates of everything that we have over here. But then there's going to be an interesting thing that we are going to see. Now, let me say y underscore is going to be equal to np dot array. And over here, just as we did with this, okay, over here we used a list, we use NumPy, but then it was almost like a list comprehension, okay? Now, what we are going to say is, okay, we are going to make sure that the output, this is dealing with the output, but over here we are saying that y underscore, okay, because we are going to use the y over here to enforce that our data is shaped in a certain way. So over here, I'm going to say that it is going to be 1 if the iteration, okay, is greater than 0, else for, else 0 for I in y. So this y we see over here is going to be the output y that's going to be presented whenever we are training the data. And we are saying I want to make sure that things don't, sorry to say, mess up along the way. So we are enforcing that anything greater than 0, we are enforcing it to be 1. Else, it was probably a mistake. We maybe did a -5 or something, so that everything will be 0, so that at least our code doesn't break down along the way. This is just some contingency measure I'm putting out over here. Without this, it is still going to work one way or the other. So now we have to, what I would say, write the iterations to now be doing this simple calculation. Okay, now this calculation is also going to be same as what we did with the predict, but this one is going to be iteratively, because over here we are going to be updating the weights to get to a very good weight. So now I'm going to say that for let me just put up a space over here. I'm going to say for this, okay, in range, and I'm going to say self.epoch because I want to have the iteration based on the number of epochs I have. Now over here, I've set a default value of 100 over here. Remember, whenever we are building our models, we can decide to choose whatever number of iterations that we have. I've set a default of 100 over here. Now, when the user is also building the model, he can decide to set any default over here, but we are saying that we want to run this loop the number of times we have these iterations. So I'll put in my semicolon, sorry, my colon over here. And I'm going to say that for the index of X, and what's going to be the index of X? Remember, you are running an iteration, and let me just show you this. All right, if we have these ones showing up over here, okay, and then there's going to be an update. The update is going to find its way attached to, I mean, the weight is what is going to be updated. So every, so to speak, inputs and its corresponding weights will be affected one way or the other. And we want to track the index or the position of where that weight, sorry, where that input is. And that's why we are saying that, okay, for this index of X, okay, and the particular I is the corresponding inputs associated with that particular weight. And I'm going to say in enumerate. Now this enumerate, I don't know if we spoke about this enumerate method over here. We are going to enumerate everything in relation to X over here. So now let me just show you with a quick demo over here so that everything we are doing makes sense. So let's say I have let's say a list, okay? This time around, let me just use a list. So X is going to be equal to, okay, let me use a tuple. Yes, I can use a list or a tuple. It doesn't really matter. So let's say I have 20, 30, 40, 50. So I'm going to use the enumerate method over here. So I'm going to, for, let's say, Y, comma, Z in, sorry, what did I do over here? Okay, in enumerate, okay, so in enumerate, and I pass in X over here. Now, if I'm to say print Y, let me use a formatted string over here so that everything looks pretty much cool. So I'm going to say Y and its corresponding X over here. And now if I run this, this is what is happening. For X and Y in enumerates. Okay, so over here, what we see is, okay, we are using the enumerate method, okay? And the enumerate is basically going to track whatever thing that we are trying to run, okay, in terms of the list, as well as its index. So you see that the Y we have over here, which is the first thing being printed out, is printing out the index. So over here, the index is 0. You know, Python starts counting from 0, okay? So upon the first iteration, the index that was discovered over here was 0. Upon the second iteration, the index was 1. The third iteration moves on and on and on. Now, the reason why we are using enumerate over here is like that, okay, let's assume these are the, let's say, the inputs, and we want to be multiplying it with its corresponding weights. We want to track the iterations in which we are and also track the actual values so that you don't end up multiplying. For instance, if this was the first iteration, the first value was 20, and we don't keep on tracking this, we may end up multiplying everything by 20. But then along the line, some updating will be done and some things will be changed. So we want to be tracking whatever thing we are doing based on the iterated value of that iteration that has been done. And that's specific to the change that we want to see. So we are seeing that for X, the index of X, which is more or less the iteration number, okay, based on whatever thing that we are saying, and that corresponding value of X based on the iterations that we are getting from the data that will pass over here. This is what we want to do. We now want to perform that same linear operation over here. Okay, so over here we can basically say that, okay, the linear underscore output is going to be equal to, once again, NP, we are using the dot operator over here. And now what do we want? We want to, remember, this is just going to track the index. Is that okay? But then this, the one going to track the data itself. And that's what we see over here. This is the first variable we see over here is the index, which is the 0, 1, 2, 3. Is that okay? And the next one, the Z. Oh, sorry. I think I made a mistake over here. It's supposed to be Z. Good. So this is what I wanted to see. So over here, we see that the Y is the index, and then the Z is the data that corresponds to that particular index. And that's what we want to track. This is what I was expecting to see, but I don't know. I still brought in X over. That's why we are getting the original, how do you call it? Tuple. So this is what we have. So based on the index, we want to be tracking the particular data and be doing the updates. Now, based on that, we are going to see that, okay, this is going to give us the actual data. So the dot product is now going to be, for instance, self.width, okay, which is something which is already generated out there. And then the I, which is going to be the actual data. And this time around, plus, of course, self.bias over here. So this one is looking good. So now the Y predicted is going to be equal to self dot the activation function. This we already know. So the activation function will come in over here and we'll pass in the linear output in this particular function over here. Now, when we do it this way, we are not quite done yet, because then what we have over here is almost the same as we predicting. But then over here, we are more interested in running through this through an iteration to be updating the weight. So this is where we come to the point where we're also going to update the weight. Now, remember this formula very well. The updates or the updated weight or the change in weight is going to be the target minus the output multiplying by our X, which is the data, multiplied by the learning rate. We've already specified the learning rate over here, and the default is 0.01. We can change it along the line, but then this is what you want to see moving on. So what I want to have over here is, okay, I want to have the update. The update is now going to be equal to self dot. Once again, let's just go back to the formula. The updates, the updated weight is going to be self dot the learning rate. So that's the first parameter we want to have over here. So we want to have the learning rate, and the learning rate is multiplying into bracket the target minus the output, multiplying the X. And the big question is, what is the target? The target is now going to be this Y underscore we have over here, because this is from that target. Okay, this Y underscore based off the index of X. And that's why we needed to track that index, because this index will tell us where we were. And this Y is almost going to be like, let me run this through a proper array. So let's say I have data is going to be equal to, let's say, np.array. And this time around, let me do, let's say a 3 by 3, okay? A 3 by 3 array. So let's say I have this 1, 2, 3. And let's say I have another 4, 5, 6, and another 9, 8, 7. Okay. So this data, sorry, is what I have over here. Now, based on what we are doing, okay, we have split this along this line, and we have made these first two inputs our data, sorry, our input data, and we have made this our output. And now we are saying that, okay, we want to run this through an iteration, but we also want to be tracking the corresponding Y, because at the end of the day, whatever calculation that we do, we are going to subtract it from that corresponding Y before we can multiply it with the learning rate to get the updated weight. So that's what we have over here. So yes, we are seeing that the target, which is going to be from this y based on the index minus, we want to get this out of the y predicted, which is what we have over here, minus the y predicted. And now what then we have to do is I can now do self dot weight. It's now going to be, this is going to be an update of that weight. It's going to be this updated version of the weight. Because this is an iteration, we have to keep track of it. And I'm going to say plus, no, sorry, multiplied by the output. Let me check this one out. It is going to be multiplied by the x, okay? It is going to be multiplied by the x. So I can now put this in this, and let's say xi based on that. And then I can also say self dot bias is just going to be the updates that I have over here. This is also going to be times 1, but then the 1 is going to be inconsequential because everything times 1 is going to be that same number. All right. So now that we have this, we are good to go. We can confidently see that, okay, we've done some few things, but then everything we've done over here makes sense based on the logic we have over here. So now let's run this and see if we can make some predictions. So I'll run this. At this point, even if there's a problem, we are not going to see. It is only when we start building the model. So behind the scene, this is almost like something Keras has written for us. And we have just been calling the function to be writing our code, okay? So over here, let's say, okay, now I want to do a prediction of some input and output of some logic gates. So I first of all need to build my model. So now I can say model is going to be equal to, and I'll call this perceptron class I have over here. So now I run this. Once again, that skeleton has been built for me. So now I then have to come and do the training, which is going to be the fitting. So I can now come and do model.fit. And what do I want to fit? Okay, I want to pass in some X and Y. So now the big question is, then I need the data. So now let's work with the data first. Okay, so let me comment this one out and let's deal with the data. So for our data, we know that, okay, so let me just do this. For our data, let's say we have X1, okay, we have X2, and then we have Y. And like I did indicate, 0, 0, sorry, 1, 1. If this is going to be the first input, let me have 0, 1, sorry. 0, 1. So this is just like you writing the truth table. And then the output we expect over here, if this is an OR gate, so let's start off with an OR gate, okay? If there's an OR gate, this is going to be 0. If there's an OR gate, this is going to be 1. If there's an OR gate, this is going to be 1. And finally, if there's an OR gate, this is also going to be 1. So this is what we have based on the physics and even the linear circuit and all those things that we know. Okay, so now the big question is, okay, where does this whole prediction and everything comes in? Now the prediction, because this is a very simple problem and you've been able to do this right from secondary school, that's why I don't see it's so much of a problem. But then the point is, okay, let's assume we have a portion of these data sets. Can we predict the next one? So the challenge I want to have this perceptron model do is, okay, I'm going to feed it with this portion of the data set and now ask it to predict if I give an input of 1, 1. So I'm going to train it with an input of 0, 0 and tell it that that corresponding output is going to be 0. An input of 0, 1, tell it that that corresponding output is going to be 1. An input of 1, 0, tell it that that corresponding output is going to be 1. And then I'll then ask it to predict. If I give you an input of 1, 1, which is not part of that training, what is going to be the possible output? And we are going to see an output over here. So now let's see how we can model this. So let's say we have the input data. And that input data, which is going to be our X, okay, is going to be np.array. So this is going to be a 2 by 2 array. So now look at what I'm going to do. I'm going to say 0, 0 for the first one, okay, then 0, 1 for the second one, and then the last one is going to be 1, 0. So I'll run this, and then it says MP is not defined. Oh wow, I haven't brought. Oh, okay. So let me bring this up over here because np dot, sorry, import numpy as np. So let me run this first over here. Let me run this again. Let me run this again. And let me run this. Okay. So now our input data looks like this. And that's exactly what I want. Okay. So I have 0, 0 for the first input. Okay. I have over here 0, 1, and then 1, 0. And now let me also get the corresponding Y output. So the Y output is going to be np dot array. And what do I want? Okay, I want something like 0, 1, 1. So I'm going to say 0, 1, 1. So let me now check out my Y output. I have 0, 1, 1. Now the big question is, okay, I want to train this with this, and later I'm going to now ask it to predict an output of 1, 1 and see if I'll get a 1 or a 0 based on the calculations that we have in there. So over here, I'm going to uncomment this. And now what I need is, first of all, I need my input data, which is going to be my X. And I also need my output data, which is going to be my Y. And now I'll run this. And I have a problem over here. It says that self.learning rate, what I have over here, predicted. I think, I don't know. I don't think there's an, I don't think there's a problem over here, but then let me see. Y minus this.
Why you were putting on this celebrating?
Is there a contribution or okay? So let's figure out the error that it says float object is not callable, and it was trying to get this learning rates, this X index minus the Y predicted, which I had a typo over there. So now let me just run this once again. So this is where we had the issue. So it says
Are you not multiplying the learning rates by the difference?
self. Oh, okay, yeah, sure. So this is supposed to be a multiplication. Very good. This is supposed to be a multiplication, and that's exactly what we find over here, because I think a lot of the time I get carried away with some of these things because you see it like we have it in algebra and you just have to bring the multiplication over here. So this is what we're missing out. So now let's run this once again, and then let's try running this. And okay, so now we don't have any problem. So some learning has been done. Now if I come and do model, now let's bring in the new data. Is that okay? So let's call this new data is going to be equal to np.array. And this new data, like I said, is going to be this 1, 1, which wasn't part of the training data. So np.array, I'm passing in 1, 1. And now if I'm to do model.fit, sorry, model.predict this time around, because I want to do a prediction over here. And I pass in new data. and run this, I get a 1 over here. And that's simply because some learning has been done. This wasn't presented to it, but it was able to make a prediction based on some calculations, just based on this perceptron that we have over here. So the mathematical foundations that we have laid up until this point is not gimmicks. It's not like some abstract thing. It is something that actually works, okay? Because in this particular instance, we didn't present 1, 1 to it. So this is completely new to the model, but it was able to, based on the learning that has been done over here and the updating of the weight that has gone through this, it is able to know that, okay, based on the, whatever values I was given, I can make a prediction out of this. Now, the interesting thing is this is a very small data set, okay? So it is able to learn quickly, just 3 inputs. The computer has that strong computing power to know. But then the point is, whatever thing we have over here is a little bit dynamic in the sense that we can have, and this is an exercise I want you to go through. Is that okay? Now have, let's say, an OR gate or an AND gate with 10 inputs. So if it is 10 input, then that means the number of instances in terms of the rules is going to be big. And what I want you to do is, so if it is 10 inputs, I wish I had something to write this on a board or something. So let's say I have X1, okay, X2, X3, X4, X5, X6, X7, X8, X9, X10. And you start 0, 0, 0, 0, 0, 1, 1, 1. I mean, those combinations, is that okay? And we get a corresponding Y. Now, what I want you to do is, once you have this, okay, you know that, okay, the data is quite huge. So you model this and probably use about, let's say, 70% of the data, is that okay, to do the training. And then you pick up some instances of the data that wasn't used as part of the training to actually do the testing. And you are definitely going to get majority correct. Some are also going to be a little bit way off. It's going to predict wrong values for it. But at the end of the day, you get the point that everything we've done so far is culminating to, okay, why we need some of these things. And the interesting thing is, when we are using Keras and TensorFlow, we don't have to worry ourselves with all this code. All that we're doing is just using some sequential model. Once we have that sequential model, that gives us the skeleton. We'll just be adding layers. Once we keep on adding the layers, we specify the parameters that we need for each particular layer. And at the end of the day, we get everything working out perfectly for us. So this is it. Please, are there any questions? I have some few minutes so that I wrap everything up. Are there any questions? Okay, Sheriff, your hand is up.
Okay, so please, when you were trying to get the shape of the data,
Yes.
you did something that I don't understand. You did data shape. Please, can you explain it?
Oh, okay. That was with the Iris data set. Okay. So let me quickly, that shouldn't be a problem at all. So what I did was, I did from scikit-learn.datasets import load underscore iris.
Sheriff, is your question what the shape is supposed to do or how it is done?
Okay, so I thought it was supposed to be maybe data.shape because we already defined data.
Oh, okay, okay. So I get where the confusion is coming from. So let me just explain that to you. So this is how I imported it. Okay, maybe how I wrote it is what brought the confusion. Now I give it a variable name of data, and I loaded this way. So the variable name I had over here was data, and I just wanted to select this one had data as its original, like, so this is a dictionary, okay, and this is the key. And these are the values. So when I wanted the data, I just did data.data. Is that okay to get this? And now when I do the shape, I was getting that shape. But then I could have used, let's say, something
You could
like
have given
iris.
a different variable name.
Exactly. So when I say iris data, and if I want to have a preview of it, I now have to say iris data in order to get this. And now when I do .data, I'm getting the actual data based on the key that I've selected. So I think that's where the maybe the confusion is coming from. Please, are you okay on that?
Yes, please. Thank you very
All right.
much.
You are welcome. Please, any other questions? Okay, so let me conclude on this and also re-emphasize the exercise I'm giving out. So yes, I'm going to share this code with you, so at least you have the benefits of everything we've done over here. The videos are going to be available as early as possible so that you can at least revise. From now till Monday is a lot of time. You can look through this. It is very simple. I think, if not for anything, I tell students that at least for about 50 to maybe 60% of everything should be understood, at least in class. The rest of it is quite normal. You just do a revision and you add it up later on. So what I want from you is, okay, based on the code that I'm going to share with you, this one, practice on your own, try and write it yourself as well. Now, once you're able to do this prediction, this one is quite simple. Now, let's give our data, our network, how do you call it? A data set that's a little bit big, okay? Our intention of writing this code was to write it for logic gates. Now, you can use this for anything that makes sense, in a sense that if the output of whatever thing you expect is either going to be a 0 or a 1, then at least this one will be okay for it. Okay, so think about a problem that you think that, okay, this one, the output is also going to be a 0 and 1. You bring in your own data, you work your way around it, and you should see results. But then at the very least, I want you to have your own data set. And when I say your own data sets, this is logic gates. So let me say 5 inputs, okay, so that it doesn't become low. So 5 inputs. So do 5 inputs for OR gates, 5 inputs for AND gates, and let's see what you get. Okay, so the 5 inputs, you write all the, if I were you, I write it on paper. Is that okay? Then I'll write np.array, then put it in this way, like the way I did it. Okay, then the corresponding output you model it. Then you intentionally leave out about 3 or 2. Okay, that 3 or 2, you can be strategic. Maybe you leave the first one out, you leave the middle one out, and maybe you leave the last one out. Over here, I only had just 3 inputs, and with just 4 instances of the data sets, I can only leave one out. That's why I left this one out. Okay, and if I had left the first one out, the model was going to be biased because everything over here is just going to be 1, 1, 1 throughout. So it will be very difficult for the model to know that there could even be a possibility of getting an output of 0. So that's why I left this one last 1, 1 out, so that at least, even if there's some biasness over here, it is 2 versus 1. And if I have a maximum of 4, and I'm already saving 1 to test my model, and I have 2 versus 1, at least in the grand scheme of things, it is not too biased based on the conditions we have over here. So maybe with the 5 inputs, you have about maybe 10 combinations. So maybe you leave the middle one out, or the second one, the middle one, and maybe the last one. You train your model, and then you use that as input to predict if you're actually going to get the actual values that you have. So please do that for 5 inputs for OR gates and AND gates. And we are going to have a discussion on that hopefully on Friday and see how things will go. Okay, so Dr. Mills, I'm done with this one. There are some few things I wanted to touch on, but then I'll leave the floor.
Okay, so what would you want to touch on?
Okay, so I'd wanted to focus on the outline that we have over here. That also, whatever thing that we've done, okay, try implementing it in the TensorFlow environment. Like I said, the TensorFlow is just the online version of whatever thing we did over here, okay? So you don't have to be even installing in. So you just type the code over here and just navigate your way around the interface. If you have any difficulty, you just share it on the platform. Some of us will be willing to help you. And yeah, so basically that's that. But then what we ended up doing is we've touched on what the perceptron truly is, and hopefully in subsequent ones we are going to see that okay, we don't really have to be writing all these code. This is just for a perceptron. No? We're writing code where we're using 20 neurons, 5 layers. You can imagine how convoluted and how complex that computation is going to be. But then this one is very simple. We can all practice our hands around this. Okay, so Dr. Mills, I think I'll end here.
Okay, so so just go to the top, from the top of your. Okay, this is this is the. I want to see where the code is starting from that side.
Okay, all right, sure.
Okay, very good. Okay, so there are certain parameters by now you are familiar with that when we are doing machine learning, we need to have something called learning rate. The rate at which we are learning. Learning here means that the rate at which we are training the network to be able to acquire the knowledge. And the knowledge here means historical data about an activity that we want to learn from. And then there is something also called epoch over here. So these two things you must be familiar with anytime you are learning, doing something to do with machine learning. Learning rate, epoch. And then the third one that you need to also be familiar with is what we call activation function. Activation function. And please, can you go back top a little on the where you have the activation function. Go down up. Oh, no. Where you were going up a little. Can go up a little for me. Up. Very good. So this is this is the activation function. And at this activation function, as we have explained this earlier on to you, that it dictates how we want the output to be. Whether we want the output to be of a two-state, either a 0 or a 1, or we want it to be a 1 or -1, 2 states. This, we can see that later on when we come back again to help us to classify people. For example, all the students on the platform, we can classify them by gender. Gender is a two-state. Either you are a male or you are a female. We don't care about the others. Either you are a male or you are a female. So because the two-state, we can use it to sort out students. The moment we introduce more ways of sorting out, for example, sort out students by department, then it changes the dynamics. Right. So things that you need to be familiar with is the epoch. And the epoch, yes, he has explained to you that when you are training the data, for example, the two input input network that he did, X1 and S2, they all have their values. So when you run one set of all the input, then that gives you just one, if you call it one iteration. Then you run the second one, second iteration. You run the third one, third iteration. So at what conditions do we stop the iteration? This is where we have to define what we call our goal. What is the tolerance level for which we want to say that enough is enough? So these are the parameters that will be coming along as we go through the development process. On that note, we will meet the next time. I'm trying to sort out if I have a few things I'm checking. If it's not going to conflict too much of my time for this week, then we can do another virtual Friday. But if not, then we'll do in-person Friday. Okay, so I will let you know on the platform. There are some things that I'm doing that is conflicting, so I will sort myself out. and I'll let you know whether this Friday we will do virtual or in person. After this, then the subsequent ones will be our virtual, our in-person, sorry. So on that note, our time is almost up. If there are no further, then we'll close. Any other further comments, questions, clarifications? Okay. If not, then we'll close. Instead of the 5, I would want us to make it 10, the original 10, the 10 input S1, S2 up to S10.
Okay. All right, sir.
Right. Okay. Thank you very much to everyone then.
Okay. Thank you, sir.